My dear students, welcome back to our channel. In this video, I will be explaining the MCA second semester subject Database Management System as prescribed by Osmania University and other universities of Telangana. We will go through the important questions and answers one by one. Let's begin with a quick revision. Unit 1 first important short question is: define a database and explain the purpose of database systems. Database and purpose of database systems. A database is a collection of organized data stored in a computer so it can be easily accessed, managed, and updated. It can store information about anything: students, products, employees, or books. A database management system, DBMS, is software that helps create, manage, and use databases efficiently. Purpose of database systems. 1. Data storage. Safely store large amounts of data. 2. Data retrieval. Quickly find information when needed. 3. Data integrity. Ensure data is accurate and consistent. 4. Security. Control access to protect sensitive data. 5. Multi-user access. Multiple people can use the database at the same time. Example: a school database stores student details, marks, and attendance. Teachers can quickly retrieve a student's marks or attendance report without checking files manually. Easy tip to remember: database is equal to organized data storage. DBMS is equal to tool to manage and use data. It makes data handling faster, safer, and more reliable than manual records. Next important short question is: 2. What are views in a database? Give an example. Views in a database. A view is a virtual table in a database. It does not store data physically but shows data from one or more tables based on a query. Views make it easier to access, manage, and secure data for users. Key points about views: shows only selected columns or rows. Helps simplify complex queries. Can hide sensitive data from users. Data in a view updates automatically when the underlying tables change. Example: in a school database, you can create a view top students to show only students with marks above 90. Create view top students as: select name, marks from students. Where marks 90. Now, teachers can quickly see top performing students without searching the whole table. Easy tip to remember: view is equal to window to see selected data. It makes working with databases faster, simpler, and safer. Next important short question is: 3. Differentiate between relational, object-based, and semi-structured databases. Databases can be designed in different ways depending on the type of data and application. Feature relational DBMS, object-based DBMS, semi-structured DBMS. Data storage tables, rows and columns, objects, data plus methods, XML, JSON, or tree structure. Schema fixed or flexible, can change easily. Suitable for structured data, complex data like multimedia, irregular, or web data. Example: MySQL, Oracle ObjectDB, DB4O, MongoDB, CouchDB. Features: easy to query, relational integrity, supports inheritance, encapsulation, handles varying structures, hierarchical data. Example: relational, school database with student tables. Object-based, library storing books as objects with methods like borrow, return. Semi-structured, social media profiles stored in JSON with different fields for each user. Easy tip to remember: relational is equal to tables. Object-based is equal to objects. Semi-structured is equal to flexible, web-like. Each type is designed for specific needs, making database management efficient and suitable for modern applications. Next important short question is 4. What are weak entity sets and give an example? Weak entity sets. A weak entity set is an entity that cannot be uniquely identified on its own. It depends on a strong entity for identification. Weak entities do not have a primary key alone, they use a combination of their attributes and the primary key of the related strong entity. Key features of weak entity sets. Cannot exist without a strong entity. Has a partial key that, combined with the strong entity's key, becomes unique. Represented in ER diagrams with a double rectangle. Example. In a company database. Strong entity, employee ID as primary key. Weak entity, dependent name. Composite key, employee ID plus dependent name uniquely identifies a dependent. This shows that a dependent cannot exist without an employee and is a typical weak entity set scenario. Easy tip to remember. Weak entity is equal to needs a strong friend to exist. It helps model real-world situations where some data depends on other data for identification. Next important short question is 5. Explain nested subqueries with a simple example. Nested subqueries. A nested subquery is a query inside another query. The inner query runs first, and its result is used by the outer query. This is useful when you need to filter data based on another query's result. Key points. Helps in breaking complex queries into simpler parts. Can return single values or sets of values for the outer query. Makes querying more flexible and powerful. Example. Find students who scored more than the class average. Select name, marks. From students. Where marks, select average, marks, from students. Inner query, select average, marks, from students, calculates the average marks. Outer query. Selects students who scored more than this average. Easy tip to remember. Nested subquery is equal to query inside a query. It helps in solving complex data retrieval problems efficiently. Next unit 1. Long questions. First important long question is 1. Explain the entity relationship, ER, model with its components and constraints. Entity relationship, ER, model. The entity relationship, ER, model is a graphical way to represent data and their relationships in a database. It is widely used in database design to plan how data will be stored, related, and accessed. Components of ER model. 1. Entities. Objects or things we want to store data about. Can be real-world objects, student, employee, or concepts, course, project. Represented as rectangles in diagrams. Example, student with attributes like roll, no, name, class. 2. Attributes. Properties or details of an entity. Can be simple, composite, full name is equal to first plus last, derived, age from DOB, or multivalued. Represented as ellipses. Example, student entity has roll, no, name, DOB. 3. Relationships. Shows how entities are connected. Represented as diamonds. Example, student enrolls in class. Constraints in ER model. 1. Key constraints. Identify a unique entity in a relationship. Example, roll no is the primary key for student. 2. Participation constraints. Total participation. Every entity must participate in the relationship. Partial participation. Some entities may participate. Example, Every student must enroll in a class, total, but a teacher may not teach a class, partial. 3. Cardinality constraints. Specifies number of instances of one entity related to another. 1 n m relationships. Example, one teacher can teach many students 1 n. Diagram example. Student class. Roll no PK class ID PK. Name. Enrolls in 1 n. Easy tip to remember. is equal to entities plus attributes plus relationships plus constraints. Entities is equal to things. Attributes is equal to details. Relationships is equal to connections. Constraints is equal to rules. Summary. The model helps visualize and organize data clearly. It ensures data integrity, uniqueness, and correct relationships, making database design efficient and easy to understand. Next important long question is: 2. Describe the database design process with an example of a banking enterprise. Database design process. The database design process is a step-by-step method to create a well-organized database. It ensures data is accurate, consistent, and easy to use. Let's explain it using a banking enterprise as an example. Step 1. Requirements analysis. Collect all information about what the database should do. Talk to bank managers, staff, and IT experts. Example, the bank needs to store customer details, accounts, transactions, and loans. Step 2. Conceptual design, modeling. Represent the database visually using diagrams. Identify entities, attributes, and relationships. Example. Entities: customer, account, loan. Attributes: customer, name, ID, account, account no, balance, loan, loan ID, amount. Relationships: customer owns account, customer applies for loan. Step 3. Schema design and refinement. Convert the diagram into tables and define keys. Refine to remove duplicate data and inconsistencies. Example, customer table has customer ID as primary key, account table has account no as primary key and customer ID as foreign key. Step 4. Normalization basics. Organize data to remove redundancy. Use 1NF, 2NF, 3NF rules. Example, instead of storing customer name in every account record, link account to customer table using customer ID. Step 5. Implementation and testing. Create the database in a DBMS, like MySQL or Oracle. Enter sample data and test queries. Example, check account balance retrieval, transaction history, and loan approvals. Easy tip to remember. RESNI. R. Requirements. Diagram. S. Schema design. N. Normalization. I. Implementation and testing. Summary. A banking database design ensures data is organized, secure, and easily retrievable. Following these steps helps banks track customers, accounts, and loans accurately, reduces errors, and allows efficient day-to-day operations. Next important long question is: 3. Explain relational databases and how diagrams are converted into relational schemas. Relational databases and conversion from diagrams. A relational database stores data in tables, relations, with rows, tuples, and columns, attributes. Each table has a primary key that uniquely identifies a row. Tables can be connected using foreign keys, which help maintain relationships. Relational databases are widely used because they are easy to query, secure, and flexible. Converting diagrams to relational schemas. The process involves mapping entities, attributes, and relationships into tables. Here's how it works. 1. Entities to tables. Each entity becomes a table. Attributes of the entity become columns. Primary key of the entity becomes primary key of the table. Example. Entity student with attributes role no, name, class table student, role no pk, name, class. 2. Relationships to tables. 1. Relationship. Add the primary key of one entity as a foreign key in the other table. 1. End relationship. Add the primary key of the one side as a foreign key in the many side. M relationship. Create a separate table with primary keys of both entities as foreign keys. Example, student enrolls in course, NM, table enrollment, role no FK, course ID FK. 3. Weak entities. Combine partial key of weak entity with primary key of strong entity to form table's primary key. Example, dependent of employee table dependent, employee ID FK, dependent name DOB. Advantages of relational databases. Easy to query using SQL. Supports data integrity with keys and constraints. Allows multi-user access safely. Handles large amounts of structured data efficiently. Easy tip to remember. Entities tables. Attributes columns. Relationships foreign keys separate tables. Summary. Relational databases translate ER diagrams into tables so that real-world data can be stored, related, and accessed efficiently. For example, a school database can have student, course, and enrollment tables representing entities and their relationships, making it easy to manage and query data. Next important long question is 4. Discuss transaction management and its importance in a database system. Transaction management and its importance in DBMS. A transaction in a database is a single unit of work that performs one or more operations like insert, update, delete, or retrieve data. Transaction management ensures that all operations in a transaction are executed correctly and the database remains consistent. Key features of a transaction. 1. Atomicity. Either all operations are completed or none are. Example, transferring money from one account to another must debit one account and credit the other completely. 2. Consistency. The database remains in a valid state before and after the transaction. 3. Isolation. Transactions are independent of each other even when executed simultaneously. 4. Durability. Once a transaction is committed, changes are permanent even if the system crashes. These 4 features are called ACID properties, which ensure reliability and correctness. Importance of transaction management. 1. Data integrity. Prevents corruption of data during errors or failures. 2. Concurrent access. Allows multiple users to work on the database without conflicts. 3. Error recovery. Helps roll back transactions if something goes wrong. 4. System reliability. Ensures that the database always reflects accurate information. Example. In a banking system, multiple customers may transfer money at the same time. Transaction management ensures Ali's transfer of 500 rupee to Bob succeeds completely. Atomicity. If the system crashes during the transfer, the transaction can be rolled back. Durability and atomicity. Simultaneous transfers do not affect each other. Isolation. Easy tip to remember. Think of a transaction like an online money transfer. It must be all or nothing, safe, and independent. Summary. Transaction management is crucial for maintaining data accuracy, security, and reliability in any database system. It ensures that multiple users can work simultaneously without errors, and all changes are properly saved or rolled back, keeping the database consistent and trustworthy. Next important long question is 5. Explain complex queries, joined relations, and how data can be modified in a database with examples. Complex queries, joined relations, and data modification. A complex query is a SQL query that retrieves data using multiple conditions, tables, or calculations. It is more advanced than a simple query and helps get meaningful information from a database. 1. Complex queries can include where, group by, having, order by subqueries. Useful for filtering, sorting, or aggregating data. Example: find students in class 10 who scored more than 80 marks. Select name, marks. From students, where class is equal to 10 and marks 80. 2. Joined relations. Join combines data from two or more tables based on a related column, usually a foreign key. Types: inner join, left join, right join, full join. Example: retrieve student names along with their class names. Select students.name, class.name. From students, inner join class. On students.classId is equal to class. Class ID. This shows how related tables can be combined to get complete information. 3. Data modification. Databases allow inserting, updating, and deleting data. 1. Insert. Add new records. Insert into students, name, class ID, marks. Values: Ali, 10, 85. 2. Update. Change existing records. Update students set marks is equal to 90 where name is equal to Ali. 3. Delete. Remove records. Delete from students where name is equal to Ali. Example: a school can add new students, update marks, or remove students who left, keeping data accurate. Easy tip to remember. Complex query is equal to smart filtering. Join is equal to connect tables. Data modification is equal to add, change, remove. Summary: complex queries, joined relations, and data modification make a database flexible and powerful. They allow users to retrieve meaningful insights, combine related information, and keep data up to date, making database systems highly efficient for real-world applications like schools, banks, or hospitals.